All right, the second page of notes for today has a couple of new concepts. We'll zoom in on that first one a little bit. It's new notation, but it is just a shorthand for taking the union of several sets in a row. Just like the big sigma is for addition, the big union symbol for I equals 1 to 3 in this example means that I fill in that variable, I equals 1, 2, 3, and I take a union of all the results. So there's what we get. When I fill in I equals 1, I get 1 and 11. For 2, I get 2 and 12, and for 3, I get 3 and 13. And the union, which is associative, so it doesn't matter which order I take those in, gives me the entire set 1, 2, 3, 11, 12, 13. You notice that that happens to be in counting order, but it's just a habit. It doesn't matter at all which order you list the numbers in. The set is the same, unordered. Here's a new one, a Cartesian product. Given two sets, you can take a product of those two sets, sometimes called a cross product because of the way it looks, but the official name is the Cartesian product. So here's an example. I let A be 4, 5, and 7, and B be 9 and 5. Then the Cartesian product A cross B is equal to the set of ordered pairs A comma B. So they look like points on the plane, which of course is the real numbers cross the real numbers. So there's an example that you may have seen before. So these are points A comma B, ordered pairs, and it's the set of all of them. So that next line shows that it's the set of A comma B such that. Sometimes you read the vertical line as a such that. A is an A and B is an element of B. So here it is for those two sets. It's all the ordered pairs where the first number comes from A and the second comes from B. So you get 4, 9, and 4, 5. Then 5, 9, and 5, 5. And then 7, 9, and 7, 5. Notice you never get 9, 5. Just 5, 9. That's because it's an ordered pair, one from first from A and the second from B. It's nice to be able to count these. Remember, we have the absolute value of a set, or the cardinality of a set. It's actually that second one. We never say absolute value for real, but it means the number of items in it. So in that example, I can see there's 6 items in the set. They're ordered pairs, they're points. So we count them separately. There's only 6 of them if you count the points, not the numbers. And that does relate to the size of the original two sets. It equals 3 times 2, which is the size of the set A and the size of the set B. That always works. The size of the set A cross B, the Cartesian product, is always equal to the product of the multiplication of the two smaller sets. So for a proof of that, this is an illustration proof. The number of pairs equals the number of the first options times the number of the second options. Those are the sets, the numbers in set A and B. And you can see how the options are chosen in this little tree picture, which is called a decision tree. First decision is the first dot, and there are 3 options, 4, 5, and 7. Those were the elements of set A. And then the second decision is when I pick the second number, but now I have to pick from set B, and there are only 2 options. Then the total possibilities are all of the endpoints, the sort of leaves on the tree at the right, because each of those represents picking 2 things, one from A and one from B. So there's 6 total possibilities. This segues into our whole next chapter, basically. Counting principles. The first counting principle, now we have an example of it, is the multiplication principle. If you have several decisions to make, and the number of options for each decision is the same, no matter what the earlier decisions are, we say they're independent, then the total number of possibilities is the multiplication or the product of the numbers of options for the separate decisions. And then we'll see some nice examples of that applied to real-world situations.